Hi, so this is the first lab of physics, constant velocity. Let's get started. Introduction. First task was to observe the motion of some object that is moving at the same speed without changing direction. After that, we compare the observed position versus time, our observed, and the predicted position versus time, our prediction, aka the computational model. Our computational model is based on Newton's second law, and equivalently, the momentum principle. End result ended up being that the prediction model does a pretty reasonable job predicting the ultimate position versus time, but there are differences due to the object not actually moving at constant velocity and some other differences due to human error. So moving on to the momentum principle, algebraically, it is velocity final equals velocity initial plus net force divided by mass times change in time, velocity being in meters per second, net force being in newtons, mass being in kilograms, time being in seconds. So assuming that our velocity is constant, and it is because this is the constant velocity lab, velocity final equals velocity initial, and we obtained our velocity initial by analyzing the video of motion in track. If velocity final is equal to velocity initial, meaning there's constant velocity, that would mean that the F net is 0. If our F net is 0, we can use the position update formula with constant velocity v to predict future positions. So, as seen here, position final equals position initial plus velocity times change in time. Here's some details of the experiment. Rolled a volleyball across the table, that's about it. Most important thing is how we obtained the initial velocity. As seen here, took the first interval of position and time, subtracted from the initial, and divided by that by the change in time to get the initial velocity. And also our axis, positive x, was to the right. So onto the discussion of the prediction. Because this is a constant velocity lab, the accuracy of the computational model is dependent upon if the object's initial velocity is maintained for the entirety of the duration of its motion. That, alongside human error, which I listed below, created some inconsistencies between the prediction and the observed. The calibration reference, aka the diameter of the volleyball, wasn't exactly measured pixel perfectly, so that could have caused some error. The motion of the object is calculated via hand click trackers, so these red dots didn't exactly track perfectly with the object's motion in the video. And in reality, net force on the volleyball isn't 0 because there's friction, gravity, among other forces. So go ahead and show the model itself, or the code behind it. Here's the mass, our initial velocity, initial position, our time interval, 0.1 seconds, and if I run it, we get this neat model and this neat graph of position versus time, or position as a function of time. And this graph comes in handy because it's this graph, but this graph has the observed motion as well. So as you can see, the model has a straight line, straight slope, because of course the velocity is constant. The observed data, in contrast, actually lines up pretty well with the model for the first 0.25 seconds or so. But as seen here, the ball slows down and its final position ends up being a good bit lower than the models. And of course this is because the object that is observed doesn't actually have constant velocity. So for the what if you were to flip the axes, what would change? The only thing that would change if we were to flip the x-axis would be that the velocity would be in the negative x direction instead of the positive x. The speed, or the magnitude of velocity, the mass, the net force, all of those remain the same. It's just that the direction of velocity would be in the opposite direction. And is it possible for you to say how many pushes and pulls, how many forces are added together to give 0 net force in the case that you observed? I said it would not be possible because this is based on Newton's second law, and Newton's second law is based on the net force. And the net force is the total force, aka the sum of the magnitude of all the forces acting on the object. It doesn't actually give the quantity of forces acting on the object. So my conclusion was no. And I believe that's it. So thank you.